Yes, good morning, students. And today we'll be working on multinomial logistic regression. Basically, uh, uh, in the previous tutorial, we learned about binary logistic regression, but this time we will be learning on multinomial logistic regression, which is basically logistic regression when number of the classes are more than two. And we will be learning some of the very classic function like the softmax function and cross entropy loss, which will be very important and essential in the modern deep learning algorithms. So make sure that you study well and understand it. So let's take a look at what we will be studying today. So we'll be learning a new function called softmax function. So recall that in the previous tutorial, we learned a function called logit function or the sigmoid function. In fact, the softmax function is derived from the sigmoid function, but for multiple classes. We also learned the binary cross entropy loss in the previous tutorial. In this tutorial, we'll modify that loss function for multiple classes. Of course, we'll be finding the gradients. And here, through my derivation, we already found that the gradient is basically the same, surprisingly. And here I have already prepared some of the code of loading the data. So today, we'll be using data from Iris, which is a data set to try to predict the family of Iris. And there are 4 classes, if I'm not wrong, using 4 features. So because we have more than 2 classes, which is 4 classes, multinomial logistic regression apply to this. And here I'm just doing the same thing. We are splitting into train and testing set. We are scaling and adding intercepts. So all of this basically the things we have done in the previous tutorial, except that we now our X and Y, the shape, the Y will be a little bit different shapes. So let's take a look later on. And what we will be doing is first we will be demonstrating that before we do anything, we have to change our Y to 1 hot. I will tell you why later on. And we'll be working on the algorithm. And lastly, we'll be showing you how to run the algorithms. Okay, great. So there's a lot to do today. Let us first work on the softmax function. So the softmax function is basically, the idea is that if we have theta tx and we apply the E function, we'll get the probability of that classes. But we want to normalize it so that we got a probability of 0 to 1. So we just simply divide it by the total sum of all the probabilities of all the classes, right? From 1 to k, right? So k here is the number of classes and c is that particular classes, right? So now I'm trying to say that the hypothesis function is basically the probability that y is that belong to that classes parameterized by that theta, right? So that is the softmax function. If you don't understand very well, don't worry. Take some time, sit down and try to dissect what is each of these numbers. It will be very useful for your future. But anyway, let us take a look at the softmax function. So given that I have x equal to NP array, okay, give me 1 second. I think I need to restart first and run all. No, thanks. All right, then make sure I have NumPy. So now I can write some code. So let's say I have the first sample which have 3 features, 1, 2, 3, and I have the second samples which have another 3 features, right? So here the shape will be m comma n, and I have 2 samples, so it will be 2, and the number of features is 3, right? So again, students, you have to be very, very familiar and very capable on shapes, because when things are very big, shapes are what keep you sane, right? So make sure that you understand that well, so we can print x dot shape, right? Now we're gonna also create y, right? And we remember that for for uh, for softmax function to work, y should be a one hot embedding. So what do I mean? Well, for example, let's say that this is a classification problem, right? So I have the first example. Maybe the first example belong to class 0, and example 2 belong to sample 2. Sorry, class 2, right? I can't do like this. If I do like this, I won't be able to calculate this softmax function, right? And you can work backward and see why. Why is that? But what I'm gonna change is that instead of like this, I will be doing like this instead, right? So that would demonstrate what I'm trying to say when I say one hot. So instead of that, I would say 1, 0, 0, and 0, 0, 1, right? So I hope you can see what I'm trying to do here. So if I have, if my, let's say my K is 3, so I have 3 classes, 0, 1, 2, and I know that the first one is 0, so I'm gonna put the 1 at here, and the other is 0, right? So this is the idea of one hot encoding, right? And here I belong to class 2. So basically 0 and 1 will be 0, and the class 2 is 1, right? So this is basically what I'm doing here. But I'm going to change a little bit. I'm going to change this to 2, and I'm going to change this to 0. And I want, if I change my k equal to, let's say 4, then it will be something like this, right? 0, 1, 0, right? So this is another example, and this is 1, 0, 0, right? Right. And it's important that we know what is the shape. So the shape of y is m comma k. So which is we have 2 samples, but we have 4 classes, right? So this would be the shape of y. So it's very important that you know that shape, right? And just give me 1 second. We forget a bracket outside here. All right. So now we know the y. Now we need the w. So for softmax function to work, we also need to have a w. So recall that in previous w, the shape is, what is the shape of w that we have learned in the previous tutorial? And you can pause the video and think a little bit, but the previous video is n comma, right? Which is we have weight for each of the feature. But now we change a little bit. It will not be n comma, it will be n comma k. That is, we will be having weight for each of the feature of each classes. So that sounds a little bit difficult to understand, but you can see that if I take the x, m comma n, dot with n comma k, you can see that this n and this n will be canceled, and you will get m comma k, right? Which is basically the y, right? So this is exactly what we want, right? When we take x dot with w, we get y, right? So that could also give you a very quick reason why w should be n comma k, right? So now we're gonna create this, right? So n w, right? And I'm just gonna create some example. So I have n, right? So what is my n? My n is basically so I'm gonna do this and make sure that I have the correct one. All right. So my n is 3, right? So I need 3 of this. right? Just to make it bigger so that you understand very well. And we got K, right? So our K is 4. So we need 4 numbers inside here. So I'm just gonna randomly put any numbers. It doesn't really matter. Usually we randomize with 0, 0, but it doesn't matter because here I'm just trying to demonstrate the softmax function. And I'm not sure any numbers will work here, right? So once we do that, we can print the w.shape and we can get 3, 4, which is n is 3 and k is 4, right? So you have to make sure that you are very familiar with all these shapes, right? And so again, review again. For x is m comma n. Even for binary is still m comma n, but for y is m comma k. But if this is a binary logistic regression, it will be m comma, right? For those who are wondering, like why for binary it does not need k, right? It can also be like 0, 0 and 1, 0, right? Well, if you have only 2 and 2 columns, actually, based on the theory of one-hot encoding, you can always delete one last column, right? So 0, 0 and 1, 0 is basically the same as 0 and 1, right? So you don't really need that last column. That's why it's m comma for binary logistic regression. For W, if this is a binary logistic regression, it's only n comma, right? And for those who always forget, you just simply find the magic shape that when you dot with X, get your Y, right? That would be something that is very easy for you to manage. So great. So now we can try to do print X at W, right? And we're also going to print X at W dot shape, right? So this is basically m comma n at n comma k. We got m comma k, right? Which is a 2 comma 4, and this is the resulting number, right? So for those who want to link back to this one, this is nothing but theta tx, right? This is basically theta tx, right? And now we have to now take a look, how do we do this softmax function, right? So according to the softmax function, we have to apply E to all this theta tx, right? Divided by sum of all the E, right? So what we can do is define a function softmax given this x, right? Which is this guy, right? Return np.exp x divided by np.sum np.exp x is equal to 1. X is equal to 1, making sure that we sum along the class, right? So here we have 4 classes, so we sum along this column, right? Because this is exactly what this she's trying to say, right? We want to sum all the classes accordingly, right? And keep thems is very important. The reason why we want to do keep thems is that once you sum, it may try to reduce the shape, and this shape is gone. You can try to do it by your time, but when we divide, we will lose the final shape, which is something we don't want to, right? All right, so this is our softmax function. So let us take a look at what we got after we do this softmax function. So x at w, right? And what I want to is also the shape, right? So what is happening here once we softmax? Well, first of all, when we do np.exp x, we are simply taking, so let's take a look how this number 6 come from, right? So what we are trying to do is basically taking np.exp 8, right? So this number come from 8. Give me 1 second. Someone call me. Just give me 1 second. All right. So I'm back. Someone call me now. So this is np.expx. So this is 8, right? And what is this, right? So, well, we can always try to run this. It doesn't matter. So we can try x at w and see what this gives us, right? So you can see that this is awesome together, and this is awesome together, right? All right, great. So what this number is giving us is basically divided by all right. So so what is this basically doing is that this one is the probability of all of these classes, right? And once you do np.exp8, you got a probability of only this one, right? But you want to normalize the entire row here so that they add up to 1, right? Because this is this represent some statistics for 4 classes, right? For sample 1, right? So you have to understand that this is the 8 is the probability that the first sample belong to class 0, probability that class first sample belong to class 1, etc., right? And we want to make this add up to 1, right? So how do we do that? Well, we add up all of them together, but we don't add up simply by adding up. We perform exp on all of them, and we got this number. And then we find the 8, right? And now we divide it. Why do we need to divide? So we can normalize them and add up to 1, right? So we can actually try to do this outside here. And we'll find how this numbers comes from, right? Let us do this. And you can see that this number represent this number, right? So yeah, so softmax function is this, right? Very, very simple. So again, let us take a look at this function. And now I hope that through the coding, you better understand what does this mean, right? So basically, you take the theta tx, right? So you take the weight, multiply with that x to transform it into some numbers, and you apply e, so it becomes a positive number, right? So because a probability is a positive. But now you have a problem that they don't add up to 1. So how do you do that? You divide it by sum of total numbers in that from class 1 to class k, right? And once you divide them, you get make sure that all the classes, when they add up together, is 1 for that sample, right? So softmax function is very, very simple, but it's very important that you understand by heart, because every machine learning algorithms and deep learning algorithms in classification domains use softmax function. Great. So now we understand this softmax function. Of course, we can try to confirm that they really add up to 1, right? So we can do softmax x at w dot sum, right? X is equal to 1, right? And we can see that they really add up to 1, right? And you can see that once I add up, this one is 1, and this one is 1, right? Which is exactly what we want. We want the probability for each classes for each of the sample when they add up is 1, right? So this is a perfect idea. Now, when we really use for inference, how do we know that? For example, one of the softmax, I got this. I don't even understand what does this mean, right? Because like, what classes does it really mean? Well, the idea is very simple. We just pick the highest number because that is the highest probability, right? So let's see. So for sample one, this number is the biggest, right? So it means that sample one belongs to class 2, right? And for sample two, which one is the biggest? Again, this one is the biggest. So it means that sample two also belongs to sample two, right? So, but we can create a very simple Python function to do that. So we can call that np argmax, softmax, x at w, and again, x is equal to 1. And you can see that for sample one is 2, and sample 2 is also 2, right? So hopefully you understand this function softmax is very important. And if you don't understand anything, just pause my video and take a look, right? So really, really important. Now, the next thing is the cross entropy loss. And in fact, if you understand the binary cross entropy loss, it should be not so difficult to understand this cross entropy loss. Please take note that this y is also 1 hot, right? Otherwise, this function won't work. So let's take a look. So let's assume that we have y like this. And let's assume that we have h is basically softmax x at w. So this is h. And now we want to take the loss function, which is the cross entropy. So this cross entropy is very simple to actually write. So we're going to do minus y. So minus y multiply with np.log h, right? I think that's it. And we also have to sum them up, right? So we're going to do np.sum. And yep, this should give us the loss function. So we can type that down and print the z, right? So that is 20. So higher is not good, lower is better. So that is how our loss function works. So if you don't believe me, I suggest you that you try to create some mock numbers of h and try to see whether it makes sense that this function is really loss function. What you want to do is to make sure that if the h is very far away, like for example, this is 1, what does this do is basically it will multiply. If this is multiplied with this, it only cares about on the 1 position, which is this, right? And if it predicts correctly, then it's good. If it predicts wrong, then it would be bad, right? So this is what this multiply does, and minus make this as a loss function. But anyway, if you don't believe me, to be convinced, you have to work the mathematics out by yourself. And once you believe it, you will forever believe it. And so try to work it out at your available time. All right, great. So this is a cross entropy loss. Now, let us take a look at the gradient. Because I don't plan to make this video too long. So I already worked out all the, again, you can go to my GitHub, the real lecture GitHub, which is basically not inside the code alarm folder, but outside. You can see that I already worked out all the calculus for you. How do I calculate all the gradients? You can take a look. And once you do that, you will find that the gradient is nothing. The gradient of this loss function is nothing but the transpose of x multiplied with h minus y, which surprisingly is the same as the previous tutorial, except that now h and y is a matrix, not a vector. So yep, so that is the gradient. Now let us take a look at our code, and Let us run this to make sure that I got this code running. So this code is fairly basic. That is the reason why I already coded this for you. So I have load the iris dataset, right? I only use the first two features so that things are easy for us. And we got X and Y. And then what I do is basically I train and test. I split the data into training and test data set. The only reason why I don't do the test train split from the sklearn is so that I can show you how do you do this manually in NumPy. And this is the feature scaling and the adding intercept, which is basically everything we have learned in the past. That's why I take the opportunity to just code it for you. Before we why don't we take a look at our X? So we have 150 examples and two features. And how about Y? So we got 150, right? So here you can see that our Y, maybe we can try to print the first 5, and you can see that, okay, maybe first 10, and we can, okay, all of them are 0, 0, which is maybe 100, and we can see that there's some Y, maybe 150. Okay, so we can see that there's a list of 3 classes, right? But anyway, we know that this Y is not in the right shape, right? Because based on our demonstration above, Y should be in a one hot format, right? So that is something we have to do in number 1, right? So let me just clear this first. And make sure I close this down so things are very clean. Now let us first work on our converting this into one hot format. So it may feel so very difficult, but if you're proficient in Python, this should not be something very difficult. But if you are not so proficient, you can follow me and try to work backward and see how do I come up with this, right? So xtrain dot shape 0 and equal to xtrain dot shape 1. Right, so make sure that I have this first. Let me just print to make sure that I have all this number correct. Right, so I got 3 classes, right? Which is 0 and 1, 2. So this is correct. I got 105 samples from the training, which is correct. And it seems like I got 3 features, right? Which is correct because I do something called column 2, so that should be correct, right? All right. I'm not so sure. Give me 1 second. That's shape 1, and yep, I think it's really 3. All right. So now once we do that, we can create a placeholder called Y-train encoder. So this is and we're going to say NP0. We know that the Y should be the shape of what? Do you guys remember? M, comma, K, right? Yep. If you don't remember this, just go up. But eventually it will be very intuitive that you know that the Y should be in this shape. So this is a placeholder. So what do we do? Well, we just do for each class in range K. If for Y-train, whenever so you have to understand what does this give you, right? So let's say this is 0, right? You can print the condition. You can see that for the first sample, so there are 105 samples, right? And what the condition gives you is that the first sample, no. Second sample, no, it's not class 0. And this one is actually class 0. So that is true. Why don't we just print the Y-train and take a look whether that is correct, right? So you can see that class 0 is right here, right? So that's why there's a true here, right? So this is what this line of code does. right? So we can delete this. So condition is basically I would say like a mass, right? Like a mass matrix that you can apply to any matrix on top. Now what you do is a Y train encoder, all right? np.where condition, right? Of that class equal to 1, right? So this may be a little bit difficult to understand. So what I'm trying to do is that for any places in which is true at that column, right? At that column, which is 0, put 1, right? And then because everything is 0 anyway, we just want to care. We just care where do we put the 1, right? So if we loop this k times, we'll make sure that all the 1 is filled in, right? So this is a very nice, nicely written code. Okay, great. So now that we got all our so let's make sure that our Y train encoder now is do you remember what is this shape? And that is n comma k, right? Sorry, m comma k, right? Which is 105, and we have 3 classes. Great. So now we done this. Let us work on our algorithm, right? And this time I will be writing as a class, because last time I think give me just 1 second. I think last time I did not really write. Okay, I write them in the function form, but not really in the class form. So this time I will be writing in the class form so that you is I think a good data scientist, you must know a little bit of software engineering. Otherwise, you will not be really a great data scientist. Yep. So it's good that you know how to make your code nicely written. All right. So now we're gonna write our class, and we're gonna just put self, and we're gonna put pass here. And what else function? What function we should put? Well, we should put fit, and we should have a function that return the gradient. Okay, we should have a softmax function. We should have a predict function. And actually, I don't think this should be h. I think this should be predict, but then there's another one that is really the predict one. That is the argmax, right? So this predict function is basically applying the softmax, and then I'm gonna have a function called plot, just for my convenience. So firstly, what I'm gonna do is the simple one first, which is the underscore. Okay, just give me. I think the one that I want to write is the simple one. It's the softmax function, because we already learned this. So we're gonna say return np.exp whatever input is this one. So this is x, or this is x, divided by np.sum, np.exp, x, comma, x is equal to 1, and I keep them equal to true, right? So this is a softmax function. It's done. I'm gonna also do the predict function, right, which is return self.softmax x and w. So in that case, I need to take in x and w. Right? Yeah, I'm not sure it's correct to put this small x, because this represent the big X, and the W. Let me just give me like h. Okay, how do I do this? H theta. Maybe this is a good name. I know this name is a little bit long, but okay, so that we don't forget what is coming in. And then when we do the real predict function, it's actually simply return np.argmax self.predict x self.w and x is equal to 1. Now that I'm thinking, actually, I should be okay. Because when we predict, we should use self.w because this is the w that we have trained. But when we actually do the internal fit, maybe we at one point we don't really know the w. So I just make sure that it always pass in the w function. I may decide to change this later on. But let's assume that this w is represent the self.w, right? But here is the real self.w that after I fit many times, I got this, right? So let us check. So this is softmax function. This is the predict function, which I take the x and w and pass the softmax. And the real predict function is basically taking the argmax and softmax them, right? And the x is equal to 1, right? All right. So hopefully that should be all right. And here I should take in the x. And to make sure that I don't confuse myself, I always remind myself that this is actually x test, right? Because yeah, but in this one, this is for predicting. I mean for fitting. So this could be x train, this could be x test, whatever. So this is a generic function. All right. Gradient. So for the gradient, let's take it x and y, and m equal to x dot shape 0, and h is basically self dot underscore predict x and self dot w, and then the loss is nothing but minus np dot sum y multiply np dot log h divided by m, right? So so the loss is average, and then the gradient is nothing but x dot t dot with h minus y, right? Great. I think I should do something. So here I want to make this h and h, so that I'm always using the correct notations. So give me one second so that I can fix all the notation correctly. So h is here, and yeah, actually it's already correct. And now I just simply return the loss and the gradient. And how about here? Did I use the notation correctly? Yeah, actually I do. Yep, everything is okay now. Great. So I think that should be okay. Now I think we are now ready to do the fit function. So for the fit function, we're going to take in the x train and y train, right? But we're going to just denote it as x and y, and we're going to create w, right? np dot random dot ran, right? And so this so this is basically a function that gives you a number between 0 and 1, and I want the shape to be n comma k. So in the init, it should create this number for me, right? So k comma n, and you should tell me how many classes there are. self.n equal to n. And of course, I want to have alpha. Basically, the learning rate. I want to call this learning rate. I have some default, which is that, and max iteration 1000, and that self dot max iter equal to max iter. Actually, now that I'm thinking backward, because now I have k and n, I can just do self.w right here, right? So that everyone knows this w. Yep. Why not I do that quickly, right? I think I should have already defined this right here, so that whenever I create this class, I have this w. And then right here, I can always make sure that this does not require to be passed here. And then I can do self.w. Right. Okay. But okay, now I'm thinking I should not do this because sometimes I may want to use a cross-validation, and I haven't checked my code yet and make sure that every time, sometimes the W may want to be reset, right? So anyway, let's keep it like this first, but you guys please feel free to optimize my code and make sure that is like even better than mine, right? Okay, great. And I'm gonna keep track of all the losses in a list. This time I'm gonna do a mini batch. And the reason why I like mini batch is because all the modern algorithms do that. So I'm gonna do start time equal to time.time, right? And I just gonna, after everything, I will just calculate all the time. And we're gonna say print f time taken. Time.time, this the current time minus the start time. All right. So within inside this, we're gonna do is that the batch size. We can manually define this, but I'm just gonna find the numbers from this. So I'm gonna just take 30% from this, and I need to make sure it is n. Otherwise, there will be a lot of problems. I'm gonna say that for I in range self.max iter. I'm just gonna do ix equal to index is np.random ran in. So I simply gonna pick one index. So what I'm doing is if you follow my tutorial, this is basically what the replacement. Yep. You can do loop all the samples, that is also fine, but I'm doing with replacement. And what I'm going to do is batch x equal to x ix plus batch size, and batch y equal to y ix plus batch size. Right. And now I'm simply do loss gradient and gradient function, batch x, batch y, right? So I first, okay, this should be self.gradient, right? Now, once I do that, I can get the losses dot append loss, and of course now I can update my w. Self.w minus learning rate multiply with gradient, and this should be self. All right. And I want to make sure that I want to print the loss. So if I 500 equal to 0, print loss at iteration. I is basically loss, right? it should be okay. Yeah, I think let us take a look. So the fit function is nothing, but I initialize a W. I I do a mini batch version in which I check mini batch and take that mini batch to update the gradient. And I do this 1,000 times. The reason why I don't use again the word epoch because I'm not using without replacement, right? If I use without replacement, I will know for sure how many that I actually exhaust all the training data, right? One question from the students is which one is should I use? Both should be fine for machine learning, but for deep learning, most people doesn't think too much, so they will use without replacement. That is, they just loop from 0 to m, and then chopping them slowly, right? Yep. So hopefully this algorithm should work. And let us, okay, we still have this plot function. And I won't take a lot of time. I already prepared some of the code. So I will just copy this and I will just hopefully this should work and then enter. So now hopefully this algorithm is now okay. Now let us do this running. So firstly, what do we have to do? We have to define the model. We have to fit, and we have to predict the X test, right? And of course, something for you to do by yourself is learn how to do inference. Like if you have some of your own data, how do you actually use your newly defined model, right? So that I will leave this to you, but let us define the model. So the model is actually logistic regression. So what do we need to provide this algorithm with the init function? So this init function is so I think we got this number k already, right? Somewhere. Yes. This is from the above here, right? So we got k. I think we also have this n. All right, great. We also have this n. So we just give n, and then that's it. Yep. I think this two is basically default. We can use default numbers, and then we'll just do let us just run this to make sure there's no problem. And we're going to do model.fit x train, and make sure that we don't use a y train. We use the y train encoder, right? So hopefully there will be no errors. And yep, there's no errors. So so it seems like the loss is not printing out nicely. It's just, of course, I just need to put 100. So I clear all the outputs and start run all. So that things are nicely. Okay, so now I got my loss. So things are slowly reducing. Now, what I want to do is predict the X test. Why not I separate them out here? And I can do this here. Y hat equal to model.predict X test. And I can print the Y hat out and see that it makes sense. So yeah, so actually we predict something. And what do we do is we can do model.plot. And we can see that our loss is slowly reducing. Very nice plot. And of course, we can also use this classification report. I did not teach you, of course, I teach you the classification report in the class, but I can teach you again just slowly, right? So what does this mean? Well, the accuracy, the total accuracy is 0.96, so it's not so bad. We are doing very well. And the precision is basically, the recall is basically focusing on the false negative, and precision focusing on false positive. And F1 score is basically the taking both into account, right? So the overall, I would say that we are doing very well. We got 0.96, right? And support basically is a sample. So we have 12 samples that belong to class 0, 20 for class 1, and 13 for class 2. We have to worry slightly because they are in balance. So in that case, when you see things that are in balance, you cannot use accuracy. You should use F1 score, right? So that is like a very simple technique that you should use. And taking a look at the F1 score, you can take the average of this, and the average is, I would say, 0.95, and that is not bad either, right? So we are doing quite well here. And the common question, should we use recall and precision? Actually, I talk a lot in the class already, but recall is mainly if you want to minimize false negative, you want to use this metric. If you want to minimize a false positive, you want to use precision. If you don't understand what I'm trying to say, you can go back to my lecture. But false positive is basically you predict positive, but actually it's negative, right? Here, you don't want false negative. That is, you predict negative, but it's actually positive. And that is very bad when it's in the something like cancer, whether you have some very bad diseases, false negative will be really bad, right? But for false positive, you predict positive, but actually it's negative. Something like search results, you return some search results, and which is you thought is positive, but actually it's negative, right? So it depends on your use case. But if you are so confused what I'm talking about, just use F1 score because it just take two into account and give a good balance, right? And here, weighted and macro average here. Weighted is basically you take the number of classes and multiply with the score, and you get that number. So weighted is basically the more if you have imbalanced class, this will be multiplied with this. This will be multiplied with this, and this will be multiplied with this, and you'll get these numbers. But macro is basically you just take all of them and average. So if you have imbalanced class, I would say macro makes more sense, right? I would say weighted actually makes less sense if you take the higher classes into account, right? But anyway, you can study more about these two numbers, and that should give you a good idea what this whole report means. Okay, great. So hopefully you understand the multinomial logistic regression, and next time we'll be learning a new algorithm. Thank you, and bye-bye.